I want to tell you about what's going to turn out to be a quantum measurement protocol, but that's not going to be apparent early in the talk, I think. That will not have applications in kind of atomic sensing realm, but hopefully have application in microscopy. So, so, last lecture I told you about this quantum measurement protocol where we were able to manipulate the noise distribution of an ensemble of atoms. And one of the key aspects of this protocol was we were able to do it in such a way that was, in some sense, non-destructive. You could call it quantum non-demolition. In this particular example, what it didn't do, what this variance reduction mechanism didn't do is it didn't destroy the quantum coherence of the system. And so in some sense, we observed something about the system, maybe the number of particles in a given quantum state, but without interacting with it in a way that completely destroyed a characteristic of that state that we wanted to observe, namely the phase coherence in the bottom. And the tool we used was a cavity. And what happened in this cavity was a beam of probe light went between two mirrors and sequentially over 100,000 interrogations interacted with this ensemble of atoms. Each atom we conceptualized as a small slab of phase shift. And by going to a regime where we were having that probe beam pass through the ensemble multiple times, I want to prompt the idea, we got into a limit where we were able to measure something we cared about that system, namely the number of atoms in the beam, without destroying something we cared about, namely the atomic coherence. Okay, so let's think about a different problem. I have a protein that's nanometer scale. Here's a rendition of the atoms in a particular protein that we've been simulating. And what you would like to do is kind of this holy grail. We heard about the kind of NV center version of this holy grail challenge earlier. We would like to determine the structure and also, in principle, the dynamics of that protein. Is it folding? How's it changing conformally? In a non-invasive way. And right now, it's impossible to do that. But kind of our tools of choice, the tool of choice is electron microscopy, and well, I should say X-ray scattering also. So what happens when those probes, X-rays or electrons, are designed to interact with such a system? Basically, they do irreparable damage. You get pretty pictures out only because you can prepare ensembles of the same protein and take many pictures of the same thing and then stitch them together with numerical methods. So if you're into X-ray spectroscopy and you follow some of the state-of-the-art X-ray sources, there's hope that maybe you can photograph these things with very high fluence X-ray sources where you collect the information from the X-rays before the thing blows up. And that's where that is going, I think, in the next 5 years. But from a quantum optics perspective, let's ask the question: can we exploit quantum measurement to devise a protocol that can take a look at this thing without mangling? So just to come to a punchline, and kind of the rest of the talk will go back and provide details that underlie the simulation result. Here is a particular protein, a small biological structure that was simulated by us and some of our colleagues at the NCEM, National Center for Electron Microscopy, where what we're doing is we're going to design an electron microscope that exploits a certain metrological protocol that's designed to reduce damage when it acquires imaging information. And so if you want to have some way of quantifying kind of the amount of damage that you inflict on a particular target, one of the key figures of merit to understand is the number of probe particles you need to impinge upon that object in a given area in order to get an accurate reconstruction of the image. And so I wish this were data, but this is simulation, and the dose, the number of electrons per square angstrom that is incident in an electron microscope configuration on this imaging area is measured in units of 4 electrons per angstrom squared. And just to calibrate that number, turns out that it's known in the community that when the number of electrons per square angstrom exceeds about 10, that just as kind of empirical fact that you can't image. You can't image a strand of DNA. It just kind of melts in front of you. And so there's a real push to get the imaging protocols working where you can reduce the dose level to something below this I won't say critical, but this known damage threshold of 10 per angstrom squared and get a good picture. And so this is a simulation using a protocol I'll explain. We call it a multi-pass electron microscopy, where the dose is below this threshold, and this is for kind of typical electron microscopy parameters. For an electron microscope, you need to know the energy of the imaging electron, the probe electron, and that's measured in kilovolts. And a high-quality transmission electron microscope runs at beam energies of about 300 kilovolts, and some of the next generation ones are running at 60 kilovolts, which say that this is kind of using kind of the standard electron parameters for current generation microscopes. And basically, we're obtaining images that are in simulation that we believe just can't obtain by conventional methods. So the protocol we're using is going to seem, when I explain it to you, is going to seem mind-numbingly stupid, and it's not going to seem quantum mechanical at all to start. And so part of what I want to explain over the course of the talk is that this protocol actually does have some deep quantum features that are perhaps remarkable when viewed in a certain context. Okay, so maybe just to also give a little foreshadowing of the method we're going to use. In a standard electron microscope, the electron phase fronts, think of them as Deboli waves, propagate through the image target here, my protein, and then there's some diffraction. The wave fronts change as a result of the phase shifts and the absorption they experience in this target, and then there's some image formation optics that form the image on electron-sensitive detector, and you go take a picture by sending lots of electrons through that and acquiring this. And what we're going to do with this protocol is, instead of sending the wavefront through once, here's we're going to go like this, and we're going to create a situation like the optical cavity where the electron wave function comes back through the protein multiple times. And it's going to pass through the thing I want to image. I'd love to do it 100,000 times like in the atom cavity experiment, but it's just 10 to 20 times in that simulation, 12 times. And what we're going to see is that even a modest number of multi-passes or sequential passes can really improve the signal noise and the kind of signal noise to damage ratio of this type of imaging. Okay, just to orient you to some of the parameters for imaging biomolecules. Here is one particular protein. It's about 10 nanometers across. Looks like a wreath. And you can characterize what that object presents to an incident electron by the phase shift that an electron wave experiences going through. What is this for an electron? This is just a voltage potential. So as the electron comes into this collection of atoms, it sees some potential, and it has to climb that potential hill. It slows down. It gets a phase shift because its de Broglie wavelength changed, and when it comes out, that phase shift is something that you would record in your imaging optics. And so for kind of 100-volt levels of potential, which is what a biomolecule like this will project, the phase shifts at 10 kilovolts, 60 kilovolts, and 300 kilovolts are much less than a radian. The higher energies that are preferred for TEM are, that phase shift is actually pretty small, just 60 milliradians. Now, the problem is that in addition to the phase shift, we also have, I want to say inelastic, but so you have other mechanisms which are going to interact with the incident electron beam. So not only going to be effect in terms of coherent forward scattering, but there may be plasmons that are launched or phonons that are launched that inelastically take energy from the electron scattered into different angles that we can consider some sort of loss mechanism. And if these inelastic events are high enough energy, then they're going to do damage to the biomolecule. And so these kind of, there's a lot of debate in the literature on which events are really truly damaging and which ones are the kinds that you can live with. But roughly speaking, if you have a 20 nanometer thick object and you put an electron beam through it, this is the ice used in cryo electron microscope, the amount of inelastic loss is going to be described by as less than 10%, about 5%. And so for an object like this, which is much thinner than 20 nanometers, you expect an electron beam attenuation, if you will, that's on the percent level or even less than that. So this just kind of orient you to the imaging problem. And now as quantum engineers, our job is to figure out a way of measuring, say, this phase shift without inflicting too much inelastic loss. All right, so now let me take you to a Nature paper, 2007, which when we first did a group meeting talk on this, we almost laughed because it just seemed like, well, why is this in Nature kind of situation? And the idea of the paper was you've got some phase shift, shifting element. Think of it as a slab of glass, which when a beam of light goes through it, gives a phase shift of 5. And what you want to do is measure 5 optimally. So I'm going to measure phase shift. My playbook is breakout interferometer. So let's build a Mach-Zehnder interferometer. Here's one arm. Here's the exit beam splitter. Here are the 2 detectors that will do some sort of harmonic measurement. And then I've got some fancy signal processing or whatever that on a single quantum basis, I shoot in the photon, I observe clicks, and I want to observe that phase shift. And what's one thing you would intuit if you were going to try and measure a small phase shift? It's like you're going to be better off having your probe particle, in this case a photon, go through the thing that's making the phase shift more than once. Why? Because as in this case, as the probe particle zigzags through that plate, the total phase shift on the beam is not 5, but it's n times 5, or I think the nomenclature we're going to use later in the talk is n, where n is the number of passes through the object. And so if, at the end of the day, I want to optimally measure phase, it makes that phase shift associated with that object makes just good experimental sense to send the beam through the object multiple times and then do my statistics to figure out what that phase shift was. Okay. So, and by the way, the beauty of this paper, so there was this kind of experimental element in it, but there's a lot of interesting quantum optics that goes into establishing how you can optimally, for a minimum number of particles, infer even the phase shift after these n passes. And by varying the number of passes and so on, there's some interesting strategies that can be employed. And so, why is this better? Well, detection noise given by the shot noise, if you will, of the photons in the detector hasn't changed, but the signal is larger because you have a larger phase shift. You go up and down the fringe by a larger amount, if you will, and that improves your signal noise. So that's a simple idea. And what I want to suggest is, let's think of this as being the biomolecule, and the probe particle being the electron, and employ the same idea. And now, from the quantum optics perspective, we have a lot of tools emerging in our toolbox exploiting entanglement. So, and the probe doesn't have to be a simple electronic. I could think of like, hey, you know what? I'm a quantum engineer. I'm going to make an entangled state of electron. I don't know how I'm going to make it, but let's imagine I could make a state of my probe electron or something. I'm going to shoot it through that ensemble and then do some really complicated quantum measurement protocol that uses all sorts of quantum information-inspired gate logic to optimally measure the phase shift with a massive entangled state. Or maybe I'm going to take a single particle, I'm going to send it through multiple times to accumulate this enhanced phase sensitivity. What's my optimal protocol? Well, Seth Lloyd had a really terrific paper back in 2006 where he essentially compared, on very general terms, these very different situations. And the conclusion was that, and this ties in with other aspects that we know about, entangled states of metrology, is that there's, compared to uncorrelated state methods, there's like a factor squared of n, where we have to define what we mean by n, either number of interactions or number of probe particles. That's there for the taking if we can properly engineer the system. And what Seth and his co-workers concluded in this article is that it's equivalent to take a single probe particle and run it through a system n times, and to take n entangled particles and to run it through a system once, in terms of your ability to measure that small phase shift. That conclusion is dressed up in some fancy theorist language, but that's the essence of this paper. So this multi-round protocol is not only something that just makes good experimental sense to us, it's also, in some sense, quantum mechanically optimal. Seems like a good idea. Let's go out and try it, see how it can work in the lab. So we started thinking about how to do this with electrons, and very quickly realized, okay, the electron problem, I'll tell you how we're going to solve that multi-round protocol problem in hardware in a minute. It's kind of challenging. Let's first see if we can make it work for optics. And you might think, like, well, that's such an intuitively straightforward idea that there must be microscopes that function on this principle. And it turns out that there are related ideas. Put the imaging particle in an object in a high finesse cavity and look at the transmitted light through the cavity. But in terms of obtaining full field images with a multi-round imaging protocol, that as an optics problem had never been solved before. So here's what Tom Schuffman and collaborators did. They built this crude microscope, which functions as follows. We have a fast pulse of light that enters in one of the mirrors it's a highly reflective mirror of a cavity. And this pulse is designed to have a duration which is short compared to the round trip time of the pulse in the cavity. So you can think of this kind of bolt of light entering one side of the cavity by part of the bullet tunneling through the mirror, and then or coming through the bead of the mirror, and then rattling back and forth, and then at some point in time being switched out. So light comes in. Here's our objectives. Here's the where we put something we want to image in this plane here. The light is made to go through the image target, which is going to turn out in this test case to be a tiny nanosphere. And then there's a pocket cell here which closes the cavity initially, so the light just bounces back and forth like so. And after so many round trips, which we can count just by timing, we know when the pulse of light was incident on this mirror, and then we know the round trip time of the cavity, and we can say, okay, if I want 11 interactions or whatever, I can have that pulse go through 11 times and then apply a voltage as pop the cell, switch the light out, and go on to CCD camera. And so then Brannon Klopper, this is what I just think is kind of you never think to see a microscope with two objectives looking right at each other. And this is before the sample state was there. These are pretty high quality objectives. I just kind of cool to see the hardware in that. This is what it looks like when there's a little nanosphere. I think it was 80 nanometers in diameter, and it was put in the image plane. And if I were just to build a conventional microscope and shoot the light through once, and then make an image of what came through, we use a dark field method here. In dark field, what you do is you block the incident beam and you detect the scattered beam. So let me draw a picture of that. The blue is one that works. So we have the incident imaging beam, and then here's the beam that the light is scattering off of, and there's some collection lens. I don't know which of these colors is going to show up, but we have lens here. Most of the light of this imaging beam sails through this lens. It focuses down, and you put a little stop there to block that. The light that's scattered, so some of the light hits the nano particle and it scatters. And it's collimated by this lens. And note that most of the light misses that block that is there to suppress the illumination beam, and then I can form an image with a final lens. Focuses this back down onto the, what the heck, it's called full multicolor. Here's the CCD. So it's dark field because the illumination beam does not hit the camera, and the only light you detect is the stuff that scatters. And so that's what we're doing here. If there's a very weak scatter, then you don't see any light making to CCD, and then as you increase the number of passes through the scatter, you see a dramatic improvement in the amount of light that's collected, and this is for 11 passes where the signal noise has improved dramatically. It's just about 100 times brighter than it was at one pass for the image, and that makes sense. If you go through the kind of Fourier optics for dark field microscopy, if this thing gives you a phase shift of phi, then the brightness of the image, the intensity that you detect is proportional to phi squared, the phase shift squared. And so if I make the phase shift 11 times bigger, I get 100 times more intensity, and that's what you see bigger. Yeah?
So eventually the number of passes I can make through the sample is limited by the reflectivity of the cavity input mirror.
Right.
And if I want to make more and more passes, I need to crank up the reflectivity, which means fewer of my fast pulses will enter the cavity as I send them in.
Yeah.
So is that what sets the fundamental limit?
Yeah, that's loss sets the limit for these optical methods. It turns out that the reflectivity of that input mirror is not really a big deal because we have we have a really bright laser pulse that comes in the front end. So
it always tunnels in?
Well, you always, if you had that as a 5/9 mirror, we would still have enough photons coming into the cavity. And if you really wanted to engineer that, you could put a pop cell in the input to just bring the light in cleanly. What sets the limit is all the other loss in this optics train. I mean, like, these objectives are good. You know, you pay your $10,000 and you get very low loss, but there's still loss in them, and likewise with the pop cell and everything else. Our round trip loss for this demonstration was about 5%.
So I should think instead, I think I'm thinking wrong about the pulse. I should think instead of the pulse is composed of some number of photons, and the tunneling rate into the mirror, the cavity, tells me how many of the photons from that pulse do make it through.
Yeah, maybe I shouldn't have used the word tunneling. I mean, it's just a beam splitter, and the photons make it through the cavity. And there's some, we have, just a whole barrel of them coming in, a trickle of them actually make it to that mirror, and we put that mirror reflectivity at 1%, which is, that means that it's a lower loss than the other elements in the cavity. It's just a convenient way of getting in the waveform. Yeah.
So is the resolution of the nanosphere limited by the wavelength of the light?
Oh, yeah, in terms of spatial resolution, all diffraction limits apply. So, it's the numerical aperture of the collecting optics and the wavelength of the light. We're using green light here, and I think it was an NA 0.8 or objective. So the resolution turned out to be around 600 nanometers spatially.
Okay. And just one more question. So you mentioned that on one of the first few slides, you mentioned that the dosage is really small in this scheme, but does the multi-pass mean that every time the electron passes through the object, does the dosage increase?
Yes. Yep. So we account in the multi-pass count, when we account for the dose, we also account for the fact that it's going through the scheme. I'll come to that. That's a crucial thing to realize. And when you have that realization, most people say the first time they see this idea, they're like, oh, okay, well, these guys forgot to account that you go multiple times, and in the end, you get more signal, but you also have more damage. And it turns out that because of a coherence effect, you actually get a favorable ratio of signal to damage, even accounting for the multiple pass.
Oh, why?
Multiple damage.
Proportion ratio applies to it.
Why is it? So you just have to run the Fourier optics on that. I don't know if I have a great intuitive explanation for that, but yeah. Which what it turns out to be. Good. So it works with the optics. That was a nanoparticle. What about something more interesting? Well, Brandon did we're going to do biology eventually, so the quantum optics version of that is, let's see if we can image red blood cells. And so here are some red blood cells. And this is not what a typical red blood cell looks like under a microscope. It's a phase contrast image of a 7-pass red blood cell. What's happening is when you see these bright and dark and bright regions is the phase is wrapping through, the total phase shift is wrapping through 2 pi. And so what we're seeing is dramatic phase shifts through the cells, which gives you a really interesting way of looking at red blood cells with this appendiform like black heads with a little bump in the middle. To show you how those images evolve, here's dark field of red blood cells with 1, 3, 5, 7 passes, and at one pass you barely see anything. State-of-the-art microscopes still resolve it because they have a lot of photons going through and excellent optics and all the rest. And so some of the beautiful pictures that you see in nature and so on, they have a tuned up enough system so that even in one pass you can see that. But if you were to instead make the phase contrast higher, then you're at 3 passes, you're already resolving the boundary of the cell, and at 5 you see that there's a little extra border in the middle, and at 7 is kind of what I showed you previously. So this is just to show that actually is useful for cells also. Here's some earlier work where we were just kind of characterizing kind of calibrated targets. You can put a hexagonal grid in the image plane and look at both the absorption and the phase shift of that grid. Here's what the field looks like after it's gone through. M times T is the transfer function. It has an amplitude, an absorption, and a phase shift term. And the math is really easy compared to what we're used to with quantum optics. You just raise that to the n power, and that's what the output field looks like. So, good question here.
Could you really go back to the last slide? So could you go back to the last slide?
Yeah, sure.
So it looks like you're just getting better contrast. It seems like your fringes should shift when you're. That seems like it's really good. Say you had a 2 pi over 7 phase delay. That one should be dark on the rightmost image,
right.
but
so
not.
If I overlaid these, like that one there, I see what you're saying, and like, if I could continuously adjust it, you would see the kind of what was once bright would become dark, and then I think you can kind of see that happening here. When you overlay that, I believe that, I believe that's what happens. Yeah. Yeah, these, I think, yeah, you almost can see, you have to use a little bit of Zen, but I think these rings do have a slight. Okay, so I wonder if we had N equal 4, you would definitely have to expect to see a bright ring in between those two. There's some other stuff in this. I wonder, maybe we should be more careful in the analysis of that. I mean, there might be some absorption here that's also happening. That's deflated phase shift. Here's a transfer electric field, and 1, 3, 5 passes. You can see through this hex grid, and this has substantial absorption. And you can see that as you go to 5 passes, the contrast just becomes really pretty exceptional. And you can see that even more spectacular way if you go into the Fourier plane and you take a Fourier transform of that light field, and you see the hexagonal structure barely visible in Fourier plane on 1 pass. Now, in terms of that structure is highly visible on 5 passes. And this was some cell that Thomas looked at initially. He was excited to also be doing something biological. He said, well, we're going to publish this. If it's a biological system, we better make the color scale green. Okay, whatever. So, and let's see, just in terms of having fun with this approach, this also, if you're familiar with orbital angular momentum beams, you can put as your imaging target a helical faceplate in the cavity that does a phase shift like this, and then so this is 0 and this is 2 pi. You put the light through that, and you make all sorts of interesting orbital angular momentum states. Because the faceplate we used was discrete and stepped, the image that we saw looked like stars, not the classic OAM beams, but nonetheless, this was what the apparatus put out was what you would expect to see. And we're just multiplying phase shifts, so there's no black magic happening. This actually, these orbital angular momentum beams turn out to be great ways of carrying information in optical communication systems. So encoding light in these types of states is kind of useful for high bandwidth communications. Okay, so now let's talk about Siglo Damage. And I have a very simple argument that, again, coming back to the idea that the ability to do damage-free or low-damage microscopy improves in a multipass protocol. So let's just go through some very simple arithmetic. All right, the multipass scattered intensity in dark field grows as m squared. And that's just because it grows as phase shift squared, and the phase shift is increasing by m, the number of passes. So the signal is going as m squared. And one way you can think of that is that there's some sort of constructive interference between the scattered waves on each pass. And I can give you the m squared effect. The inelastic loss, the damage, is just growing linearly with the number of passes. So you take the ratio, signal to damage, and you can see that you win as a linear function of number of passes. That's the essence of the method. And it's kind of interesting to take this perspective, this analysis, and reflect back to the cavity QED system I presented yesterday. Because that was a system that also had good signal and low damage. We scattered 10 to the minus 2, 10 to the minus 3 photons per atom, but we're able to observe a substantial phase shift that allowed us to non-destructively count the number of atoms and to actually observe the quantum state of the atom without collapsing it. And I think it's exactly the same physics which is at work. There's the fact that on kind of multiple interrogations, the elastic shift is growing quadratically, if you will, and the damage, the inelastic, is growing linearly, and in the end, you win. Okay, so that's what happened with light. of what can we do with electrons. Good. So, by the way, electron microscope is just an awesome technological feat. This is something out of there's a rendition of this at the Deutsches Museum in Munich. If you haven't been to that museum, it's an awesome science museum. These things were built in the 30s, and we're taking, you know, kind of pictures of tiny stuff since then, as the technology has been perfected over the past 85 years. And it's a really remarkably mature quantum technology. Because, you know, it's hard to understand how a TEM works without understanding quantum mechanics. And so, if you want to point to a quantum technology which is really awesome, that's out there doing good, electron microscopes are such a technology. All right, now, question is, can we improve an electron microscope with a multipass? So we started talking to people up at the National Center for Electron Microscopy in Berkeley, and at first they were skeptical, and then I think they became converts. The skepticism arose from that Siglo Damage argument that you kind of alluded to earlier, and then when you go through the math, eventually you're forced to conclude that those arguments are correct. And so this was a simulation that Colin Ophis, who is a truly gifted kind of electron microscopist, put together describing the method. The electron comes into the cavity. These are the electron mirrors. Here's the protein, and these are lenses that kind of manipulate the image formed in the electron wavefronts. The electrons go through here multiple times, and then are exit, and our image is formed on the screen. And that simulation image I showed you earlier is a multi-slice image of, which means you consider the thickness of the thing you're looking at. Was an image stitched together with the rules of electron propagation through matter by Colin. And I don't have too much more to say about the methods he used, other than say that they were sort of having proven out in other simulations of electron microscope systems for, I think, maybe a decade. And so let's take a look at some of his simulation results for some interesting small stuff. So here is one very small protein. And this is these are strands of DNA, kind of entwined in this funny conformation. And it's impossible to see this in a conventional transmission electron microscope, but in simulation, this is what is seen. On the vertical here, the columns are labeled by the number of passes of the electron through. The effective dose is the total dose, including the multi-passing. And this is done for this object and this star-like object. And you can see that when you go up to 16 passes with a very low damage, the quality of that image, and this is, maybe you can quantify that quality by its your ability to find features in the thing you're imaging with kind of what do I want to say? Some official metrics. You can also just look at it eye by eye and say, hey, that image there looks just about as good as that image there. Here I had 16 times the dose on only one pass, and I look like I'm getting just about the same information as what I get when I go through 16 times with a much lower dose. And the point is that you would never be able to see this in reality, because if you put 128 E per angstrom squared on that kind of protein, it would melt in front of you. Right, so this says, hey, maybe it's possible to see single exposure images of DNA at low Coulomb gamma thresholds. So let me talk a little bit about what the technology that's needed to make this work. First, you need a pulse of electrons. So how do you get a pulse of electrons? Well, one technique is to use a fast laser triggered photocathode. No, I don't need to turn on my time card. I committed the crime of leaving the internet on here. So here's a tip. In comes a fast laser pulse via something like the photoelectric effect. The pulse comes in, pushes out an electron. That electron then goes into the rest of your electron optics and into the cavity and into this multipass scheme. So that's how you get the fast pulse of electrons. How do you make a cavity for electrons? Well, this is an interesting situation because with optics, you always confront loss. I mean, every time a photon touches the surface, there's a chance it gets absorbed or scattered in a way you didn't want it to be scattered. In electron optics, it's just electromagnetic fields that are doing the damage in terms of redirecting the electron beam and so forth. And so the loss is in principle extremely low. You have Bremsstrahlung radiation as the electron is slowed down and re-accelerated by a mirror, for example. You can calculate that for parameters. It's nothing. This might be one of those configurations where the optic situation is actually less favorable, much less favorable than what you might imagine doing with electron optics. And so how do you make a cavity? Well, also with a cavity with electron optics, it appears to be straightforward to create a situation where you can gate in a pulse of electrons just by lowering a barrier, and then just by applying a voltage pulse that has to be like a nanosecond long, then the electron can rattle. This is a 1D simulation of something that's obvious, representation of something obviously three-dimensional. The electron bounces off this barrier, and by the time it comes back, you've raised the gate. We call this the barn door cavity. It rattles back and forth, and then it exits. The challenge is to design this cavity so that it maintains the integrity of the electron wavefront after multiple passes. And so that's something we've been collaborating with some state-of-the-art electron microscope companies. Here's a barn door. It's just, I don't do well in it. You have some electrodes. You have to shift the voltages. You have to do so in a way that doesn't create stray electric and magnetic fields that otherwise deviate the electron beam in a natural way. And this can all be understood by simulation, I think, before we build. So here's a simulation of a design. Here's the design, the test design we built that was big, and everything kind of checked out. What else is there? We were naive enough when we first, have the idea, and you're like, oh my gosh, we're going to non-destructively image proteins. Let's go build an electron microscope. So we went to the kind of the off-the-shelf manufacturer for electron optics, Kimball Physics, and we put together this electron microscope column. It looks like a rat's nest with wires. I mean, one thing I learned is you got a lot of voltages flying around in an electron microscope, and so it's something best left to the professionals. But we tried to do it by hand the old-fashioned way as experimentalists the first time. And we were able to see electrons bouncing back and forth in our cavity. This was one mirror, this was another barn door. We weren't trying to image anything, we just wanted to see could we gate an electron in between two electrodes, have it bounce a few times and then come out. And it did that, but not much else. It was sort of useless for microscopy. The electron was the transverse wave function and so forth. So we went and started talking to pros, and they helped us figure out how to design the column officially. It's kind of like you're going into lab and say, oh, you know what? I need a lens in my laser beam. Oh, I know what I'll do. I'll go get a piece of glass and grind the lens. We would never do that. That's what we were trying to do with that cavity previously. It was like just a silly thing to try. So we went to people who actually can grind the glass for the lenses, and they're now helping us make the cavity. This is what an early prototype diagram looked like. You have the gun, you have all sorts of other optics that make sure that the wavefront aberrations are not too out of control, and projection lenses that after the electron exits the cavity go onto your detection screen and so forth. And this thing is all being, you can simulate this with software that costs you $30,000 a seat, and this is showing us that we should be able to maintain excellent blur, beam blur, for like up to 10 passes in the column we're designing. And this is kind of what the electrode structure looks like. And MEB stands for Monroe's Electron Beam Software, $30,000 a seat with the academic discount. And you can't live without it. I mean, it's just this guy is understood how to do the finite element and make sure there are no errors in your propagation paths with the electron trajectories and so forth. So all the state-of-the-art electron microscopes use this guy's software. And finally, it's being built. So this is DeLong Industries in the Czech Republic that has finished the gun and the power supply for the gun that's now building the column for us. And hopefully in a year or so, we'll be trying out this microscope. in the lab. So, I wanted to say, yeah, great. I wanted to say a few more words about quantum mechanics in this imaging protocol. And I think this is where it gets conceptually pretty interesting. So, let's just consider in the abstract a dispersive, weakly absorbing object. The phase shift is phi, the absorption coefficient is alpha through a single pass. And now we're going to go through that object m times, and we're going to look at some of the signal sizes. So first, as I stated earlier, the dark field signals scale as the phase shift squared. So in the limit where the phase shift is larger than the absorption, there is an absorptive component to the signal, but we're going to neglect that here. The dark field signal size is given by that simple expression. If I say I want to detect that object, then, and here the name of the game is, I don't want to take a pretty picture. I just have something in the sample area, and I want to send in a stream of probe particles, and I want to know, is that thing in my way? Right, so I have a detectability threshold, and I'm going to say that the way I get a minimum number of detections, this is, if you will, a probability of detection for a single probe particle. And so say this number, after I put my n and my phi, is still less than 1, then the way I can detect that is to send in many probe particles, one after another, and eventually the detector will go click, and I will then know that there was an object in the way at that location. And my detectability criteria is that the number of probe particles times the probability per click is on the, that should be a squiggle sign, it's on the order of 1. So that's how I learn that there's something in the way. And then you can say, well, what's the damage? And the damage done is basically, for each probe particle, I have m passes with coefficient alpha, and then I have n particles total. The total damage done is going to be n times n times alpha. And then I can just do a little bit of manipulation, and I can write n in terms of m squared and phi squared, and I can find that the damage it can be written per detection as alpha over m phi squared. And you put in experimentally relevant values for alpha and phi, the phase shift for these imaging objects, like the protein, and what you find out is that the damage can be much less than 1. All right, so what does that mean? As I just been, kind of mixing quantum pictures and semi-classical pictures in a reckless way. But what this means is that I can go into an experiment. I can take my required n electrons and shoot them through the microscope, and I have the small phase shift and absorbing element in there that I want to see. And like, let's say n is 10. Then 9 times out of 10, I will not suffer, per quantum mechanics, 9 times out of 10, I will not suffer an inelastic loss mechanism. And I will detect the electron, or I detect the object by looking at my detection criteria, you'll see that my detection criteria is met. I will detect the object 9 times out of 10 without suffering one of these inelastic losses. 1 time out of 10 is a terrible situation. That electron scatters into some horrible angle, or one of the number of electrons I need to send in there scatters to a horrible angle, and I know I've killed the thing like that. 9 times out of 10, I see it. Now, how much damage have I done to the image target those 9 times out of 10 where I'm good to go? Now, thinking classically, I would say, well, I've done a little bit of damage each time. So I've done 1/10 of damage on every one. But not quantum mechanically. Quantum mechanics is saying that, like, those 9 times out of 10, I have essentially been damage-free. And then when I 1 time out of 10, it's catastrophe. But those other 9 times, that's a pretty good situation. It's not like I've done a little bit of damage. I've done no damage. All right, and this go, no go aspect of quantum mechanics is a feature that we're used to exploiting in other contexts. And so here is where I think you have a very powerful lever in terms of imaging. Yeah?
But if you're using n photons, electrons,
Yeah.
then that probability just says that 1/10 of n is what's interacting.
1/10 of those. If n is, it gets a little more complicated to think about it when n is greater than 1. Yeah, so it might be simplest to start off just thinking of n equals 1, in which case I think you're sold. And then if you say, okay, now I have this train of 10 of them, how do I think about it? You have to be a little careful about what you've detected with the other 9 like if you didn't have the probability of it scattering out and going to your screen, then in the dark field method, those other electrons, if they didn't suffer inelastic loss, are just going to hit your dark field block, and you're going to want to make sure to detect those ones just so you don't split up. I don't know. I think that answers your question, but yeah. This is a general category of counterfactual measurement, and I want to remind you of a really cool situation that was conceptually illuminated by Melissa Rubin back in '93. And that is, let's say you want to detect an object like their thought experiment was a bomb that with a photon. And the rule of this game is if the photon impinges on that object, it's a trigger and the bomb explodes. All right, so, but you want to detect that bomb without ever triggering the bomb. Well, they noted that using counterfactual type of arguments, that by building an interferometer that was initially aligned, so if there's no bomb this is the bomb, if there's no bomb in that path, if you align this interferometer so that every time you send an input photon, this detector goes click, then, right, that's the initial condition. Now you come and say, okay, I'm gonna put a bomb right there. Then some of the time, the first photon will come in and it will split in 2, if you will. Some of the time, there will be probability that will come down this path of the interferometer and the photon will actually hit the bomb, and the bomb will go boom. And so that's maybe not so interesting. But some of the time, photon will go through this path, and by virtue of this path being blocked, now the photon comes to this beam splitter, and there's a 50-50 probability of the photon coming back to the detector or that detector. Some of the time, detector D2 will click. That is cool. Because if D2 clicks, the photon wasn't absorbed, but the only way that detector could have clicked is if there was a bomb in the arm. So you have non-destructively detected the presence of that bomb with this measurement protocol. Now it only succeeds a fraction of the time, so as a practical technology it's sort of useless, but conceptually, that's really fascinating. All right? And what I want to argue is that the same sort of thing is happening in the multipass protocol I just described. Now, let me add another layer to this. When we first started this program, we didn't exactly think that this simple multipass protocol was what we were going to use. We had in mind something more complicated. And this was based on what is known in the literature as interaction-free measurement, and here's a reference for that back in '95. The idea is, can you think of a quantum optics configuration that improves the efficiency of that bomb detection from like 25%, which is what it was in the original scheme, to something closer to 100%. And the plan to do that is something that I'll describe in the context of electrons. Let's imagine I have 2 cavities that are coupled with a beam splitter, so that the probe particle, namely this electron or it could be photon wave function, oscillates back and forth between these cavities, but this cavity, every so often, this beam splitter puts coherently a small fraction of the wave function into another mode. And schematically, I've drawn it as an entirely different cavity. And these two cavities are chosen so that their resonance frequencies are exactly the same. And basically, as the probe particle oscillates, it coherently transfers just by you just solve out simple coherent addition of wave function, if you will. And after so many bounces, it's got 100% probability of being in the other cavity, at which point you can have a detector here, and the detector goes click, and when there's no click there, you would know that there was no object in the cavity. Now, the kind of cool thing happens when you put an object in this cavity. Then, on every pass through this beam splitter, you push out just a little bit of the wave function that's supposed to hit that, but then it gets absorbed by this pixel. But you just pushed a little bit of the wave function out, and so that it doesn't do quote much damage because there's very low probability of this thing actually creating the bomb. But if you kind of take quantum Zeno type ideas, this wave packet is just oscillating back and forth. It never gets the coherent buildup it needs to find this other cavity path. So no object in this vertical cavity. And what happens is you send photon or electron and it ends up here. Object in cavity, and you find out that it never ends up there, it always ends up there. And the damage you do is basically 1 over the number of passes in the cavity. And we thought this was going to be the good scheme for us early on, and it turned out it was just hopeless to figure out how to build this in terms of the electron optics. But if you go through the damage analysis, what is kind of neat is if you consider this is another way of thinking about these nested cavity situations. You can show the damage for this protocol, which is what I've drawn here, is exactly the same as what I did previously. You can show that the damage scales as absorption divided by aphasia squared and 1 over m. And what's interesting to note, and this is another thing that we first really had trouble accepting when we were designing, when we were arriving on this multi-pass protocol configuration, was that this maybe conceptually cleaner situation had exactly the same figures of merit for the damage probability as did the much simpler to implement multi-class configuration. In this configuration, I need to figure out how to make 2 cavities with couple mode and all the rest. And in a single multipass, it's a very straightforward optics layout. And so you say, we were originally going to build this, but then you figure out that other multipass configuration seems to be working pretty well. So why not do that? So I want to finish with 2 slides that I hope you're asking questions and not trusting what I'm telling you. Because it's one of those things, often when you look at quantum systems, you say, like, that seems like it's too good to be true. This seems like it's too good to be true. I'm describing an imaging method that addresses a holy grail. I'd be like, maybe I can totally non-destructively image a biomolecule. So is that too good to be true? And so we floated this idea to a lot of the leading electron microscopy groups, and we got a lot of feedback. And feedback, the toughest challenges or questions that we had to answer came in 2 categories. And so I want to kind of finish this presentation with these issues. So one is the question of coherence. In some sense, I need to preserve coherence for the electron wave function as it goes through the imaging target multiple times. As I'm doing wave addition in my math, so I've got to figure out that I can add up waves. And somebody who's familiar with electron microscopy, which we weren't when we started this, say, well, anytime you go through anything, you are going to suffer a little bit of inelastic loss. For example, if I take a coherent electron beam and I go through just a crystal whose function is to diffract, it's going to lose energy. If I come in with 10 kilovolts worth of energy, after it goes to that crystal, I'm going to have 10 kilovolts minus epsilon worth of energy. All right? And so you might think that that energy loss is something that's going to wipe out the transverse spatial coherence that's required to make this work. Here's a really neat, beautiful experiment that kind of rules out that line of thought. So it's an electron holography apparatus, and what happens is, in comes a beam of electrons. The beam of electrons diffracts off this crystal and gives two coherent wavefronts that are interfered with this. This is a metal wire, which is called a biprism, which what it does is it's a great kind of way of and building up interference patterns. This is like one arm of a Young's double slit, and this is like another arm of a Young's double slit. And here's a position-sensitive detector here, actually. And here's a filter that looks at the energy of the electrons as they after they've gone through the crystal. And you might think if there's energy lost for the electron going through the crystal, that somehow gave which path information that's going to wipe out the possibility of interference. And you will not be able to see interference fringes, or this is, they call this electron hologram, at the detector. And what's amazing is that if you go to tune this energy filter for zero energy loss, you see beautiful fringes. If you now go to the minus 18 electron volt peak, this is an energy loss spectrum. This is no loss, and then these are the amount of energy that's lost by some of the electrons. You tune that to the minus 18 volt peak, where there's been a pretty dramatic inelastic event happening in that crystal. It happens in such a way that these two paths remain spatially coherent. And that's shown in this picture here, where you still see interference fringes even after an 18 volt plasma loss. Right? So if there's something in the target that's going to take a little bit of energy away from the electron as it's dropping through, I don't think it's going to be a problem per this data. Another objection, and this is my final slide, is like somebody said, like, oh, that's great, but you're never even going to be able to you're not even going to be able to see an image, because as the electron goes back and forth through the sample, there's going to be so many of these minor energy loss events, plasmon scatterings and whatnot, that beam is nowhere near possible of having the same energy as it had when it came in initially. And so you won't even be able to form an image, let alone do damage-free. And so here's another kind of proof of concept work from the literature that kind of makes you believe. And by the way, when these kind of questions about coherence and imaging capability of electron microscopes, they're also there for single paths. Like, and if you start thinking quantum mechanically about how an electron microscope works and about which path information and all the rest, you can quickly convince yourself that you will never be able to see any images whatsoever. And so, of course, we know that's not true. And so in this really cool paper, they were just looking at some lab 6 at zero energy loss, and they see the kind of atomic scale structure, and then they went to the minus 25 volt energy loss, which is characteristic of what we kind of would expect to see. And you also see excellent images. So transverse spatial coherence, which is what we need, is preserved in this protocol, we think. So we hope it's going to work. We're building it now. If it does, I think it's going to be a really interesting way of thinking about the interplay between quantum mechanics and imaging that might actually have some practical utility. That's all I have to say. Thanks.
Maybe I get lost. In the beginning, we said we want multi-patterns to be more sensitive to the phase difference.
Good.
Then later we mentioned the quantum Siglo effect to avoid the damage of the sample.
Good.
So if we use quantum Siglo effect, can we still get multi-patterns?
I should be careful. In quantum Siglo effect was by analogy. All right. So. And one of the issues with the traditional kind of quantum Zeno or interaction-free method for electron microscopy was it seemed like it was going to be very difficult to get to realistic operating parameters for the kind of that coupled mode scheme to work. The multi-pass method that I described earlier it kind of is immune to some of the issues that you would think plague you for the conventional interaction-free topology. So I guess my short answer is, sure, I can multipass through. I have something that's a weak absorber and a weak phase shifter, and I'm just going through it multiple times. And then I do the math and say, well, how much signal do I get out of that when I do a dark field imaging, and how much absorption do I get? And I get into this interesting quantum regime where I can take a picture, but with the damage probability, which is less than 1, which is, by the way, right now when you take a picture, that damage probability figure in there is much bigger than 1. So, that's the essence of the argument. I don't know if that works for you or not. Did that address your question?
Yeah, I have another dumb question. Like, for me, like quantum data, in fact, it can measure the existence of the object, not the phase. Is that true? What we want?
Yeah, this is, so, correct. And so this is, what we're optimizing against here is something a little bit different from that. So maybe I'm just arguing by analogy to quantum data. What I'm showing is that the multipass method gives us the same signal damage metric as a quantum Xenon implementation. And then somehow I want to make the top level point that, that this idea of multipassing is somehow quantum mechanically very efficient, and that traces back to the Seth Loy article and also to what we do with cavity QED and other quantum measurement protocols.
A lot of the analysis that you showed in the lead up to this analogy to the cavity started with the assumption that you have essentially a phase object, mostly that's weakly absorbing, right? How accurate is that? Because electrons get really absorbent, samples get really absorbent to electrons really fast as you get thicker and thicker. So how realistic? What kind of limit does that put on you? Because if you start encroaching in that limit, then as you pass through your sample 10 times, then there's not really much left to do that.
Yeah, excellent. So let me show you what the sample stage we are designing right now with some guys at NSEN. What we have in mind is 2 sheets of graphene separated by 5 nanometers. And then the thin protein is sandwiched between those sheets in an aqueous solution. So when we started this, the people who prompted us to think in this direction, Moore Foundation, said, we want you to image a living cell. And we were stupid enough to think that we might be able to do that. And then you go and you take your arguments, you say, like, well, electrons actually get absorbed when they go through stuff. The only way this works is if the amount of stuff in the way of the electrons is tiny. And so it just turns out to be kind of lucky that for 5 nanometer graphene liquid cells, which the whole world is figuring out to make, it's actually, you talk to people who make these, and it's as you take one graphene sheet, you put your stuff, you put the other graphene sheet down, and that's it. And the water doesn't leak through or whatever, and you put that in your team stage or whatever, and you're good to go. So that's what we want to use eventually. To start off with, we're just going to try and image some hard target, like something with holes drilled in by an electron.
So I don't know too much about electron microscopy, but how do you make a coherent beam of electrons?
Oh, yeah, excellent. How do we do it? What you do is you have the source of electrons is this, and by the way, okay, these tricks evolved over almost a century. So the source of electron is in the highly coherent microscopes is a field emission tip. And it's a pointy piece of metal. Tungsten is usually chosen. There's some other materials like that are a little more esoteric, but let's stick with tungsten. That's crystallographically aligned. And then at the very edge of this tip, you have electrons. And in the conventional view of that, let me plot the potential that an electron sees as a function of this coordinate z. Here it's in the metal, and then there's a work function, And now let me apply an external electric field. So I have something that, some electrode here where I put a voltage on that produces a slope potential that looks like this outside of the metal. And then because of the Schottky effect, this actually turns out to bend. And the electron is sitting here at the Fermi energy. And what it does is it tunnels through this sharp metal tip. Now, because it tunnels through a very small spatial area, these tips can, in principle, be atomically sharp. In practical electron microscopy, they're like 30 nanometers round. Because that's so sharp, it turns out that the electron wave function, when it tunnels through, is transverse, has a lot of transverse coherence. And so that's how you make an electron wave function that has excellent transverse coherence.
Shouldn't they also be phase coherent for capturing phase information from the sample?
So, so let's talk about what type of phase coherence we want. So, in a laser beam, oftentimes you think about longitudinal coherence and you think about pure frequencies, so that the phase at one point in time can be used to predict the phase at another point in time. One of the attributes of the scheme that we're analyzing here is longitudinal coherence is not a requirement. If the phase longitudinally as this propagates changes, that's okay, because that's an arbitrary phase that affects every point along the image plane. What really matters to us is the transverse phase coherence. In other words, to the extent to which the phase at this point in the beam is equal to the phase at this point in the beam as the beam propagates. And that's what that tip gives you. And then our challenge or the Long Industries challenge as the designers of the electron optics is to design a column so that that phase stays coherent as the beam propagates through the cavity. And then what we're measuring is the relative phase between this point in the field and that point in the field, and that's how we form the image.
Another question is, so when you have the cavity and you want the electron to get out of the cavity, just reduce the gate potential, right?
Yeah.
But then can there also be tunneling effects that the electron comes out when you don't just at another
yeah.
time?
So it turns out that is very hard to get into a regime where electrons can tunnel through those potentials. We had hoped we could find a regime like that. You have to make the width of the potential barrier ridiculously narrow and ridiculously shallow, beyond state of the art. So the barriers are, for all practical purposes here, completely classical. Yeah. And it's just you go through the numbers for WKB tunneling.
Yeah, so at the beginning of the talk, you kind of motivated imaging small-ish proteins. And you also mentioned kind of looking at protein dynamics.
Yeah.
So if I use this sort of like graphene fluid cell,
Yeah.
On one hand, I'd be really excited that I get to image a protein directly in aqueous solution, because I could think about running a catalyst inside solution and watching for, at different spots in the sample, I might be seeing a protein in a different ligation state or something like that. But in the case of a 5 nanometer thick cell, then you're drastically limited in how large of a protein you can stick in there, right?
Totally.
So in this kind of scheme, would you be able to look for different mechanical states of proteins, or is this too thin of an iteration?
So I'm not the best person to answer that question, and but I have been told by people who should know that there are classes of protein where this is remains very interesting.
And you'll have the resolution to see those small ones?
Totally. Yeah, according to those, that's the output of those simulations. You know, at some level, it's pie in the sky, because first we have to see what happens statically, and then you know, there's some people who point out that those damage thresholds are just the ones that are there to tell you the threshold when you don't literally melt the thing when you're looking at it. But you know, if you're talking about something like protein folding, there's a big difference between melting it and preserving function. And so maybe the damage threshold to preserve function is much lower. And that's just, the literature's all over the place on this, and you know, I would say it's really just a prime for experimental input. So yeah, so I think it's, you know, it'd be great if it all worked out. You know, we started taking movies, that would be living the dream. And we'll probably be somewhere in between that awesome endpoint and hopefully the endpoint of it doesn't work at all.
And about the blood cell, talk about, so instead of seeing that's the like the phase transition, I think it's more about the information about thickness, because it's, for blood cell it looks like a pie, so it's thick at the edge but thin in the center. So the field or round means we are the center is too small to be detected. So that that shape like really tells us the information of thickness.
Yeah, I mean, if we have not done any refined analysis, and this was just, I mean, like the level of thought behind this experiment was Brandon cut himself, put his blood in the slides, and I want to see if I can see my cells, so it happens. And I suggested to him that, like, okay, maybe we should, be a little bit safer. So, we have not traced back and done a more quantitative analysis, and based on your question and kind of what you're suggesting here, I think that's probably a really interesting next step. What kind of information can we extract from those images, and can we learn something that it's hard to learn right now.
So I'm still just like a little confused about like the photon bomb analogy.
Yeah.
Just like kind of, I guess, talk about that.
Yeah. Okay. So the idea is, so in the photon bomb analogy, when detector T2 went click, I detected a photon, and the bomb didn't go off. Right now, the only way you think that you could detect the bomb is to have a photon hit the bomb, and so you would think that any time you want to make a statement that you were detecting the bomb won't have necessarily exploded. And so, using this idea of counterfactual measurement, which I think really fits very nicely into the formalism that Klaus told us about yesterday, where you have a whole bunch of information and you aggregate that information to see what you can learn about the quantum state of the system at a particular point in time. Here it's just kind of amazing that with this click on detector D2, where the full photon was detected, that I can make an inference that the bomb was there. You want to say that the only way you can detect that bomb is to explode it. Okay, and what's the physics behind that? The physics is just exploiting quantum interference. That and basic projective measurement. And so now go to the multipass microscope. All right, and I described a method where when I run this multipass protocol, and I might have to do that by putting in a stream of particles, a few number of particles, but let's just for conceptual simplicity say I get to a situation where I can put in one probe electron and I can run enough passes through that object so that if there's no absorption, I will get a click on the screen. Then, and the screen, that click will only happen at a position where that object was placed. Then, if the screen goes click, and then in a dark field imaging, the only way it goes click is if it was diffracting from that object the full time. Then I have detected that object, but without exploding that object, without the bomb going off. The bomb going off is one of these highly inelastic absorption mechanisms where you lose, kind of maybe even more than 100 volts worth of energy for the beam, which is, 100 electron volts is a lot of energy. It's breaking bonds kind of situation. So now I go and I calculate what's the damage probability in the multipass method, just using known absorption cross section. And I say we can get into it, interestingly, I can get into a regime where I can both have like unity probability for detecting the thing, or close to unity, and a small probability for having the bomb go off or the thing explode. That the probability for explosion was 1/m for the parameters of this problem. So this means that, if I have that m be like 100, 99 times instead of 10, 99 times out of 100, I will send the probe particle through and I will detect the presence of that object without ever destroying it. Not even just a little bit, because I got, my mechanism is such that it's an all or nothing type of wiping out the the object. And take 1.5 times out of 100. Forget it. That little protein's toast. We're going to ship that to the protein graveyard on the slide and go on to a new protein and take a look at it. I didn't get any information out of that 1 out of 100 protein that exploded. But the other 99 times, which I can certify that I did not do any damage to it because I'm detecting the electron at the screen, not somewhere else in the system. The other 99 times, I know that I didn't do any damage to the object by just the logic of quantum measurement, this very elementary counterfactual argument. You know, a lot of people like to say, what is the essence of quantum mechanics? What are the experiments that are, tell you something is truly quantum? And the Young's double slit is one experiment that's cited. It's the fact that you can see single particle interference produced. And I also think this kind of, obviously this probabilistic, all or nothing aspect of detection is another purely quantum hallmark. The fact that these events are described as probabilities and Born rule, that's the essence, that's an essential quantum feature. And so this measurement protocol is kind of exploiting both of those foundation principles, and I think an interesting one.
My advice would be that if you want to learn more, simply do not Google this phrase, the photon bomb.
It's a very interesting literature. It's really it's just almost like fighting words. The notion of interaction-free and measurement that doesn't appeal to many people. And there's a really interesting literature foundation of quantum mechanics that describes this. You can, and the way to talk about it safely, just like non-demolition measurement, to me it's all semantics, and as skilled users of the terminology, we can recognize when we're dealing with a semantic issue. It's some combination of coherence and quantum Zeno and projective measurement in this counterfactual regime that's doing the work. And then you might want to say it's interaction free, you might not. You need an interesting literature on that.
Any more questions? Join me in thanking Mark and all of the lecturers. I would like to also thank the lecturers who came throughout the week. They spent time and gave effort really from their daily activities, duties back in their home institutions to talk to you and sit with you, and hopefully you've gained some from interactions with them. While we do not measure you for what you have learned, I hope you feel a little bit smarter than last week. So thank you all for coming.